first of all, none of the technology is behaving itself. We'll just cross our fingers, hope that it all does sort of the right thing. Projectors, recordings, everything is not working properly, but hopefully it will work sufficiently well. Okay, so where were we? This morning we spent a bunch of time thinking a little bit about why we maybe want to study fairness and prediction, and then we spent time with two possible ways of describing fairness or ways of setting a fairness kind of an objective. One of them just said, hey, give the positive rating to the same fraction of people in all of the protected groups. Another of them was a little bit more subtle and said, let's match our false positive rates across the groups, let's match our false negative rates across the groups. We had problems with both of these. Fine, moving on. Let's get to a third notion that we might investigate. It's another one of these group fairness notions, meaning it's something about some statistical desideratum that we're going to try to enforce across various groups. So the cluster of notions here get known as sufficiency kinds of notions. What's the idea here? Conditioning on R. What was R?
Prediction.
The prediction, yeah. So conditioning on the prediction that we give, we want independence between what and what?
Protected attribute.
The protected attribute, that was the A, and what was the Y? The true label. Okay. So what does that mean? Conditioning. This is a weirder one, right? This takes a minute, right? Conditioning on the prediction, I want independence between the protected attribute and the true label. So I'm going to claim that one way to interpret this is it's a requirement that the scores that we give, those R's that we produce, be equally meaningful across the groups. So back to our example of trying to figure out who we're going to give loans to, we would like the probability that somebody who actually repays the loan, conditioned on them being female, and our algorithm having given them a high score, to be similar to the probability that somebody's going to repay, conditioned on them being male, and us having given them a high score. So that high score should have similar ability to predict the desired outcome in the male group and in the female group. Okay? So making this a little bit more general, we're going to say that the probability that you are truly of type 1, conditioned on any score that we give, should be similar across the groups. So the another way to sort of interpret this is again with this graphical model representation. So it's this R thing now that's doing the mediating. Different statistical condition.
So when you present the graphical model, what do you kind of like? How do you interpret it? Like, is it like an ideal state of the world where this fairness notion solves the problem? Or?
Yeah, okay. So like, I don't want to get deeply into all the causality stuff that I have a feeling you might want to be going into. So I'm not going to say anything that's saying that the world should behave in a certain way or that the algorithm should behave in a certain way. I'm just giving you a statistical requirement that one might impose on an algorithm that generates R's. You could then take it in a direction to talk about causality and to talk about the truth state of the world. I'm not going to go there right now, but maybe if we have time, we can sort of reflect a little bit on causality as we go on, because it's an interesting direction. Yeah?
Would this thing be interpreted as matching rock curves?
So this thing can be I'm going to go, I think, where you want to go in just a slide. So let's hold that thought for a moment. So this can be interpreted in this way of saying that the meaning of the score is similar. What do we like about this?
Well, it solves the problem of reds and blues.
Okay, well, yeah, say more about that. What were you disturbed about before that maybe this is helping us with?
Me? Wasn't too disturbed.
Okay. Okay, so but what were you referring to? What was somebody else disturbed about? Yeah.
Okay, like it's like when we have the same expectations for red and blue, we may still have different distributions, and our previous approach didn't capture that essentially, and this one does.
Yeah, so this is, this sort of has this effect of saying, if you have different distributions in the population, that's fine. We're not going to make that break our predictor. We're okay with the predictor saying, positive more to women than to men, or vice versa, if that's reflecting reality. So it's sort of addressing some of the concerns that we had with the previous concepts, but it's a little less familiar as a fairness notion in some sense. We don't see this as, immediately giving us a sense that, we're treating the two categories or the many categories equally. It's a little...
Does it in a way generalize that notion?
No.
No.
We'll get to the interactions between the various notions in a moment. So if I had to put, sort of advantages here, this is a relatively straightforward concept to ensure, to audit. We're not going to talk too much about algorithms today, but we have nice algorithms that achieve these kinds of guarantees. I think of this as also having the property that it incentivizes collecting better data, because in some sense, if I don't know how to make good predictions on a subgroup, then this will potentially incentivize me to figure out why not, why I'm doing a bad job of sort of predicting repayment in some subgroup. The thing that people like most about this is that it's not at odds with accuracy. What do I mean by this? That this is a constraint that, first of all, if we had perfect prediction, would be satisfied. But
Is perfect meaning ones and zeros?
yeah, good question. What do I mean really by perfect prediction? Because I like to go back and forth between whether we're in a binary world or whether so here if we had just to keep it simple, yes, let's say both the predictions and the payments for a moment, just to complete this sentence, are going to be binary. If we had the perfect ability to predict on all of the individuals in our population, then great. Our predictions would not be more or less accurate on one of the populations. Great. But beyond this, even if we don't have the ability to make perfect predictions, enforcing this is not going to be forcing us to sacrifice accuracy like our previous notion was. So with our previous notion, if we had difficulty in some sense in predicting on a subpopulation, then what did we have to do? We just had to make intentional mistakes on other populations, and that was really unsatisfying. And here, with the sufficiency notion, all we're constrained to do is we're constrained to have the same sort of level of sort of meaningfulness of the scores across the various populations. This is yeah, go ahead.
Sorry. So here I can no longer say that I'm just rejecting everybody.
So you could give everybody, in some sense, the average score. You could, and that would be acceptable here. That would sort of meet this. But you'd have to give the. I mean,
The right
But
average
very
here.
inaccurate.
but very inaccurate. Yes. And if you want to push more towards accuracy, then you're going to, in some sense, give finer grained predictions.
Give different.
Yeah. Question. There are a few questions here. No, first. Yeah.
There's something interesting here. So I'm looking at myself as a user of this type of algorithm. I really like this condition because it tells me, oh, I can use the output simply because I know it will mean exactly the same thing for men and women. And this is a type of point of view from the user of our algorithm that we didn't have in the last two definitions.
Yeah.
I wonder if there's like a way, like incentive compatible output, or I don't know.
That's a great question. I don't know of a formulation of a question that exactly matches that, but it's worth trying to think about that a bit more. Yeah, it's definitely taking a different perspective in the sense of the thing we're being normative about in some sense is a different piece of the system.
Right.
Yeah. Yeah, that's a great, I think that's a great point. Other questions, thoughts? Yeah. Sergio, did you recover yours?
Yeah, no. The last two conditions, you have three variables, y, a, r.
Uh-huh.
You take one and you say the other two are independent condition on the third. There is a third one. I think, so we had condition independence given A, that was the previous slide, right?
Yeah, so we had a
No,
condition
given
on y
y.
before.
Given y,
Before we just had the independence, the
Okay,
first,
so
you want to
given-
ignore the
given
first one because that was
y-
just an independence
so
condition.
I'm trying to wrap my head around. So
Yeah.
given y, r and a are independent, now
Yep.
it's given r.
Now given R, y and A
Okay.
are independent.
Now, does it make sense to say given A, y and r are independent? Or that's completely outside, I'm trying
You
to.
sort of want R to reflect Y.
Yeah, our goal is for
that
R
and
to,
and y should be in fact
reflect-
correlated as much as possible, so the third one doesn't
the
make
third
sense.
one doesn't
Okay, cool.
feel great to
Okay.
me as a goal.
No,
Yeah.
no,
Yeah.
Noam is right, sounds like an anti-goal. Okay.
Yeah, but exactly, this is in some
Goal
sense the game.
me, self-goal.
Exactly. So this is I like that. Yes. So this is in some sense the game that you want to play here, though, is to say, like, we can specify all sorts of statistical properties, which ones match with something we might be interested in, and what's good about them, what's bad about them, and eventually how do they interact with other things we care about. So okay, so we're here. There was another question, comment. So this is the sort of least familiar looking one. Oh, before I say my cons, what do you not like about this? Other than it's a little less intuitive, maybe. Any thoughts that you might not, things you might not like about this as a notion?
Assume that y and a are really independent.
If y and a are really independent, we're in this world where we shouldn't be discriminating.
Where
There's
really
no
there
benefit
is-
for
A is
accuracy.
really irrelevant, A is really irrelevant to the distribution of A.
Mhm.
Uh,
Then this is easy.
Then it is automatically satisfied by any R.
A.
No.
No, I could pick an R that depends on A very intentionally, stupidly. It's a
So, sorry,
It's
any
a-
R, any R.
That ignores
R
the A.
That uses A is going to, that uses A in a non-trivial way is going to introduce unfairness in some sense. So that's, so in a world, in an ideal world where A does not affect Y, R should not affect it either. That's a desideratum somehow that it's on top of everything, which I hope all these conditions satisfy. I don't, so for this is clear. I don't know about number two. But again, each one has to be checked carefully. But there should be a desideratum that I think one may want to put
yeah.
for extreme
Yeah.
cases.
There's a comment that was spotting. Okay, what do you not like about this? Other than it's a little unfamiliar. Yeah.
That's the problem with the high score component, because your high score can still be, your observation of something like that can still have a lot of encoding in it, and it can still be affected by data, it can still be affected by distributions. So, this basically says, like, assuming you have two independent distributions, and we just look at them as their own sort of independent way, and you want them to be independently good, and we decide independently good for female is X and independently good for males is Y. At some point, you have to reconcile the fact you're mixing the two populations.
Well, it does some reconciliation in the sense that the high score has to mean the same thing
Yeah.
across the two
how
populations.
do
So
you
it
define
so
what
it
means
does
the same
that.
thing? So how do you
Um,
define what means the same thing? So for repayments, a really good example is women statistically were getting smaller loans. So the loss given default was much lower, the probability of defaulting is much higher. So how do you mean the same?
Yeah, so one of the things that's going on here is, in some sense, the choice that you get to make here is how you bucket people according to the various scores that you get. So if I'm thinking about designing this algorithm that needs to achieve this, I have labels or scores that I can give to people, and so I'm putting people into buckets. And one of the things that you might not like about this is that my choice of how coarsely to bucket this can have a big impact that could look unfair, because I could choose to bucket much more coarsely in one population than in another, potentially. So I think this is, at some level, all of these things may not capture what we mean by fairness, and in particular, this is an issue that I'm going to return to. This is a notion that can be, all of these notions actually can be, in some sense, gerrymandered, in the sense that I can, on paper, achieve this, but you will look at it and you will see that I've chosen to bucket people in a way that makes you unsatisfied, and we'll get there in a second, but yes.
Relatively easy to ensure an audit.
Mm-hmm.
Now, you don't observe why. You observe whether, in the end, what proportion of those have repaid or not. Now, could be that that everything was fair given your data, but all of them came from Ohio, and in Ohio something happened, and now nobody's repaying it.
Yes.
And then
Yes.
you are going to say, wait a minute. So, in some sense, you want to audit when it is run, not when it is realized. But when it is run, you have no idea what Y is. So what does it mean to audit it and ensure it at auditing stage?
Yeah. So in order to
it's
do,
a practical question. I mean,
it's a good question. So there are a couple of things I think to say there. So one of them is, usually when we mean auditing, we mean that we're going to have to get some data that the algorithm was not trained on, but where we do have pairs of Y's and X's, and we also have access to the A's.
Oh, so like half the
And
data
then-
you train,
So you
half
can
the
do,
data you check, which you have all the
exactly,
data
you could do
on.
that. I mean,
I
or
see. Okay.
downstream, we're
Okay,
gonna
that's a
we're
good
gonna
answer.
construct a
Okay.
situation where we're gonna be able to do something that resembles that. But you're absolutely right. If I don't have access to Y's or A's or both, then I'm in trouble for auditing. And this is a true real-world problem: is that in many cases you don't have that kind of access, or it's problematic for various reasons. Yes.
And so I'm confused here. So
Mhm.
what this probability means, let's say we forget about A. Then R is prediction, and what we say is if we predicted 0.6, we want to be right in like 60% cases. Like it should be 1 in 60% cases. So it's like unbiasedness in a sense.
It's gonna go there in a second. It's not quite there, but what I think you're saying is that, wow, this reminds me a lot of calibration.
Yes, but A should not have predictive power beyond what is already in X. So as in A should not, like conditioning on A, if our data is unbiased, in our model, it automatically satisfies. I don't see how it imposes an additional constraint with our model.
Right. So this is when we go to the calibration version of this, which sort of simplifies the story a little bit. I think it'll feel more concrete. And then let me return to where I think you're trying to go here. So
Can
yeah.
you repeat the problem of gerrymandering? I didn't understand the problem.
Yeah, so the gerrymandering problem is a problem where actually maybe I have a slide that looks gerrymandering-ish. So the gerrymandering problem is a problem where you can bucket groups of people together to get something
I
that's
just didn't understand why.
so here in the context of fairness, for example, I would call this one example of a gerrymandering issue. So I'm being fair in terms of white versus black, because I've sort of drawn the line in a way where that I've labeled, the right percentage of
Proportion of green is the
proportions
same
of
above the
green
line
and
and
the same.
below the
I
line.
don't want to tie myself too closely to one of the fairness notions, but you can do a version of this for each of the fairness notions. I'm being fair with respect to male versus female, but I've managed to create my buckets of how I treat people so that once I look at the intersection, it feels like there's a deeper issue that
So
I've...
the buckets is where you draw the lines?
Yeah. Yeah, so
okay.
in my mind, the buckets are sort of how you choose to make this distinction. Not where you draw the lines. The buckets in terms of how I've chosen to label people. So I have not chosen to label people in a way such that I respect this intersection of identities.
So greens are like the wrong labels.
Greens are like the good outcome or the bad outcome.
Okay, because
Um,
usually the way I think about gerrymandering would be how I draw the line.
You're thinking about the physical world where you're drawing the physical
Yeah.
boundaries. So here the choice that we get to make is which people we put in which labels.
Okay, good.
So those are our analogy to the physical boundaries. It's not a perfect analogy.
No, I
Maybe
understand
the
now.
analogy to gerrymandering is less than helpful. Okay, but let me go back to calibration because I think this is going to help. So in calibration, we live in a world now where we're really talking about binary outcomes. By the way, if anybody wants to figure out the air conditioning, we can do that if anyone's getting warm. We live in a world where there are binary outcomes, and it's an attempt to move towards interpreting these scores that we're giving people actually as probabilities, which is, I think, exactly where you wanted to go a moment ago. And so what calibration says is that we're going to require that for all score values that we might give people, so all of these R's that we might give people, that the probability that you're a true positive conditioned on the score is exactly the score. So if we look at the bucket of people to whom we give a score of 0.6, 60% of them should actually be true positives. If we look at the bucket of people to whom we give a score of 0.1, 10% of them should actually be true positives. This is calibration, and it looks a whole lot like where we were at before, right? We were saying that, we didn't give it this equals R thing over here, but other than giving this equals R thing and doing this funny conditioning on group membership, we have the same thing going on here, right? Okay, so let's line that up again. So now what we're saying is we could say a score satisfies calibration by group if we also condition on the group membership inside that calibration notion. So we say that for every group that you might belong to, if we look at the people who get a label of 0.6 in that group, then 60% of them should actually be true positives. That should also be true for every other group that people can belong to. So,
Except that, the equal R is not something you have in your model. Equal the same, what you say is equal R prime. What matters is the same I prime for all A, that's all. Doesn't have to be the right,
Exactly,
R,
so-
doesn't matter. So long as you do the binning right, you have to do the binning right, that's all.
yeah, so what we said for sufficiency is that we didn't care that we had the equal R,
Yeah.
but
Just
calibration...
just equal something.
Exactly.
Constant.
Equals a constant. So calibration by group immediately gives you sufficiency. It's this stronger condition that says we have an R here. It turns out it basically goes the other direction too. If you have sufficiency, then all you need to do is relabel your R's in order to get calibration by group. And this is actually pretty straightforward to see. So maybe I won't walk through this slowly because I want to get to other places as well. But basically, what this is take your thing that has sufficiency. There is a relabeling of your R's, like a post-processing of these R values that gets you exactly where you want to go in terms of calibration by group. Okay.
Calibration, you can even do it online. That has nothing to do with this. But now you're doing it offline, which is fine. But you can even do it online in real time.
It actually does have to do with this at some level, because if you want to think about algorithmically how to get these guarantees, then that becomes relevant.
Okay,
Yes.
when you get to calibrating, that's fine.
Yes.
But this is saying that like
Are you
I
funny?
can be good in terms of this fairness by like for one group I just give them the average score and don't put much effort. For the other group I can very exactly be more fine grained and then everything will be the
Yeah, so I think this is, in some sense, where you're going here, is that basically sufficiency is often sort of automatically satisfied. If you're doing rich enough sort of unconstrained machine learning, then basically you can, what you're trying to do is you're trying to optimize your score function in some sense when you're doing this machine learning. And that optimal score function that you're trying to get to is calibrated. So if you have rich enough data and rich enough sort of class of models that you're learning, then you get the sufficiency criteria automatically, and you get this sort of group-based sufficiency criteria if you have access to the groups, either explicitly in the data or implicitly encoded in the data. So in some sense, this is disappointing as a fairness notion, because what I'm saying is, it's not demanding much more beyond accuracy. On the other hand, if you're not getting it, it's an interesting red flag. And you should understand why you're not getting this calibration. Noam, you look like you want to...
I mean, I think it's more than that. It's not just accuracy, but also that you relabeled the outcomes in the correct way, in an equivalent way. Right? It's sort of condition on the post-processing of your categorization. That you give it the correct label and not the incorrect
The
label.
meaning stays the same, the labeling changes, that's all.
Right.
That's
Yeah,
exactly.
but that's a requirement that you give consistent labels to different groups.
Yeah, but
Yeah,
that's
yeah,
a trivial step.
Yes.
So that, yeah. So, if in practice you go and you try this out, if you have rich data, and you have, rich machine learning, you see in practice that often you do automatically get good calibration across groups. This is something that you can just see happen often. So maybe it's not so satisfying as a fairness criterion. It's not demanding much. On the other hand, in situations where you don't have sufficient richness, you can get yourself into trouble and you don't necessarily see this calibration in practice. So you can think of calibration as in that way, appealing or unappealing. I think it depends on your perspective, but this is exactly the problem that we were chatting about before. If you think about what can go wrong with calibration, it can be exactly this issue that I can decide to give group 1 the average. I can decide to be very, very precise on another group. We'll be happily calibrated in both of them, assuming I got the numbers right. But yet it feels like I'm being very unfair, for example, to the good guys in the red group. Because why are they all getting treated the same? I have rich enough information to do differently. I have rich enough information to do better.
Again, so if I take it from the calibration literature, what you want is not just calibration, but you want the meaning to be as refined as possible, so you should go to the Breyer scope, which encompasses both of them.
Interesting. Okay, the literature hasn't gone exactly there, but that's an interesting direction to consider. There was something that was heading towards a question? Okay. So I'm going to say a few more words about all these notions, and then we're going to start to put them into interaction with each other. Okay. So you're not happy with any of my fairness notions. That's fine. I told you wouldn't be. But maybe you still want to use these sort of as interesting red flags. And maybe you want, if you're seeing that your algorithm on your data is not satisfying one of these notions, you want to go in and understand how you might go about enforcing these fairness notions. And generally in the literature, there's sort of clusters of literature around 3 main approaches here. One of them is messing with the data in some way to try to ensure that the subsequent learning process is going to maintain the property that you wanted, whichever statistical property you were interested in. One of them is as part of your learning process, you try to enforce this constraint or goal of one of these statistical properties. And another is post-processing. So you take a classifier that is broken according to one of these statistical properties and you try to fix it. And there are literatures about all of these. We could talk about pros and cons and issues with all of these. There's a ton of work there, and I don't think that's maybe the most important thing. Group fairness definitions don't fix all the fairness problems. You guys mentioned some of these before, but I just want to acknowledge that before we continue to dig in on the group fairness notions. None of these notions seek to remediate historical injustices. For example, if we see differential loan repayment and people in protected group A really do repay the loans at a worse rate, but it's not their fault because of some history they've, encountered. This doesn't model that in any way. This doesn't attempt to fix that problem in any way. It just says, oh, they repay at lower rates, then, we should bake that into the model as part of our statistics. The intersectionality / gender gerrymandering issues we talked a little bit before. You need to consider sort of rich intersections of identities if you don't want to end up with sort of this hidden discrimination where I'm okay with respect to blacks and I'm okay with respect to women, but whoops, black women I treat very badly. All of these, as some of you have alluded to, depend on observational criteria. These are all functions of things that I can measure or have access to. There may be other things that matter. In particular, there may be other factors that are involved causally in the outcomes that I care about that I'm just not observing and not modeling. And the really bad news, these group fairness notions are generally at odds with each other. And that's where we're going to go now. So you didn't like any of them, but maybe you were hoping, okay, now the news is going to be, well, we just ensure all three of them, and they each sort of have their pros and cons, but then we get all of them and we get all the goodness. No, you can't have any pair of them. Sorry.
So everything's independent. That one part. That comes from.
Yeah, so exactly. So we'll see exactly where sort of these pairs of concepts run us into various sorts of trouble. Questions before we go and do that? So now the part where we cross our fingers and hope that the technology will allow us to switch devices.
I have a short question.
Yeah.
When you talk about gerrymandering, for example,
Yeah.
do you assume that like the system designer has some kind of like a malicious intent? Like, could it be that they're just like benign? They want to maximize their the accuracy of their algorithm, and therefore they are not like they won't reach those situations?
It's a great question. I think the literature is a little informed by sort of the CS worst case mentality, where generally there's sort of this feeling that if there's somebody who can take advantage of a loophole in your definition, then they will. So that tends to be sort of the mode of analyzing these kinds of things. It's an interesting question if there's a good way to sort of model natural analysts and circumstances in some way and just say something more positive there. Nothing of that flavor comes to mind. It doesn't mean that literature doesn't exist, but it's certainly not the main mode of thought.
Mm-hmm.
Yeah, that's an interesting point. Yeah.
Isn't it also kind of just saying that you don't have to be malicious? It's more like if I'm training something, like maybe this is the easiest thing to learn, and you could have done better by just doing it, by just taking, like a few more precautions. But like you didn't try to be malicious. It's just like I wanted some amount of accuracy. I got it. I stopped. Didn't check anything else. I could have just checked something and could have still gotten the same accuracy, but like I wouldn't be gerrymandered because this was somehow a local minima that I got stuck into.
Yeah. So, I mean,
Like, there's no malicious in it. Like,
I actually think that all the bad examples that I gave in the beginning from the real world, those were all cases where there was good intent. I don't think anybody was trying to be unfair. I don't think there was anything malicious. I think it was all about accuracy and sort of a blindness to fairness issues. So you could give that as evidence that maybe it's good to be sort of in this worst case mindset. Then the question is whether or not there's a specific sort of model of a situation where maybe under certain assumptions you don't see some sort of worst case behavior emerge. And I can see that there's maybe room for doing that kind of analysis. I just don't know of something that looks quite like that in the literature today. Okay, great. So what we want to do now is sort of the bad news of various combinations of our fairness criteria. We'll see how far we get in this particular game, and then at some point we'll say, okay, we understand bad news all around, and then maybe we can move on and sort of talk a little bit about where else the literature is going these days. So let's maybe start with a relatively a relatively easy version of this. In all of this analysis, I want to make an assumption, which is I want to assume, is this actually working? Yes. You're allowed to complain about my handwriting. And actually make it more clear. It's really okay. We're going to assume that A and Y are not independent. Why do I want to assume that?
That's not the right thing to do.
Yeah, we don't have a fairness problem if the sensitive attribute has nothing to do with the outcome, right? Then really we don't have any concerns about fairness. This is an easy situation. So I want to get to a place where there's a little bit of subtlety, and the sensitive attribute has some implications. And so we can't just, toss it out and say it should be irrelevant. Yes?
Although I think it is worthwhile to mention that the actual thing we are worried about socially is that when A and Y really are independent, but people have biases. And this is really what we want to protect from. And now we've gone to this second order kind of thing. Oh, maybe there is some conditioning, what do we do? The real human problem is that even though they're independent, people will have biases. Right?
That's a great point. Very well taken. And what you're saying in some sense, Noam, is sometimes we have a problem and it could be solved even by our first definition of fairness, which is just be independent of the sensitive attribute, guys. It's irrelevant. Stop relying on it. And then we said, okay, fine, that's insufficient for all situations. That's kind of the easy problem. Let's move on to more sophisticated situations. You're absolutely right. I mean, in the real world, we got people running around relying on the sensitive attribute when it's totally irrelevant for various human reasons. Computers would be good at not doing that.
Yeah. Right. Yeah. When they are independent, and you have to choose at random some subset, then you should not make it dependent on anything that is visible. You should really do an IID draw for everyone, whether you give them the loan or not. Because in principle, you could say, I can only give 10 loans out of 100. How do I choose 10? Okay, I choose
In a
the
way
first 10
that's independent,
The first 10 alphabetical. It turns out, that all of them are males. That's not good. So you can't do that. You're not allowed to do that. You have to, in some sense, do an IID draw for each one.
Yeah, related
That's
to
what
our
fairness would be.
sampling issues from before. Okay, so setting that as assumption aside, first let's do sort of a relatively easy one: independence and sufficiency. Okay.
No, you have to remind us.
Yeah,
which
exactly.
one
I have to
is
remind
which.
myself which these words are not evocative
Yeah,
enough for me. Okay, so what do I mean by independence? I mean independence are independent of A. Yes? What does that mean?
Unconditionally.
Unconditionally. What does that mean?
Means that the
Your
prediction.
Prediction should be independent of the sensitive attribute. Okay? And then the sufficiency one was where we start to get into this world of conditioning. We said that Y independent of A conditioned on R. Okay? So writing these again in our language from before, the probability that R is equal to some R given A equals A should be equal to the probability that R equals R given that A equals
Or
B.
just the probability that R equals R. That's it. You don't have to say anything.
Yeah. We have a
The
universal.
total probability.
Yeah,
that's it.
exactly.
That shows that it doesn't depend on small a.
Exactly, and then we have over here in the sufficiency world, we have a probability that Y equals 1, given that R equals R, and A equals A, is equal to, again, we could write this in various ways, that R equals R, and A equals B. Okay, so we have these two things. Now we want to claim, you can't have them both. Why not? Any intuition?
Yes, you can, if Y is a constant. You can, if Y is a constant.
Okay.
Y is independent of A. We have assumed Y is not independent of A.
Yeah, so
Why the constant?
there's a reason I
No,
Then everything, all the
No,
independence
but
constant.
assumption is
Everything
Y
is
is,
independent of a constant.
No, the assumption is that A and Y
Yes.
are not independent, and if it was a constant,
Oh,
they would be.
then they will be independent, right, I see. Oh, under that assumption,
yeah.
okay.
Yeah.
So-
That's sorry. This is the global
Okay,
universal
so that-
assumption.
that was,
you
you know,
lost it
few
already. It's
minutes
okay. It's
ago,
okay.
so I
Yeah. So I wanted to avoid the trivial solutions.
Yeah, okay, good.
So why? So my handwriting did get really bad. You're supposed to complain about that. Sufficiency and independence. I can't have them both. Why? What's going on here? What are they each doing for us? Sufficiency is saying, you know, we're going to do this labeling independent of the A's. Sufficiency is saying we're going to do this matching of false positive rates, this matching of false negative rates. Yeah.
Yes, we have like left is independence, but on the right we have the dependence of A on R, like through this condition. So that's, I think.
I feel like this is getting you into trouble somewhere. Yeah.
Would that imply that A and Y are independent or not? If both,
Yes.
if both
Yeah,
are
yeah.
both simultaneous.
Yeah. Yeah, so that's exactly where we should get into trouble. So let's play with it and see what goes wrong when we try to assume that we have both sufficiency and independence. So let's say we're going to do this by contradiction. Okay. So then if we pick two groups, A and B, that we care about, let's just look at some things that we know. So the probability that Y takes on some value, given A is a member of A. Well, we can write this sort of summing over all of the R's, all of these predictions that we make, right?
So we're moving from binary?
No, it doesn't.
We don't need binary right now. We don't need.
It's the same.
You wrote the one and
Yeah.
your Y.
Yeah.
If you do
Sorry.
And I don't
Yeah.
care, but let's speak.
No, you're right. You're right. We don't actually need binary. For this,
It's independent. Just show the properties are.
binary is going to make my life significantly easier a little bit later on, where I'm not sure I get everything else for free. But for now, we don't need it. But if you want to live in a binary world, that's, I think, a totally legitimate way to do the rest of this conversation. Okay, so now I want to sum over all of these predictions that I can give to people. So that's the probability that Y equals Y and R is R, given that I'm a member of group A. And now I just want to sort of pull my R into the conditioning here. So I want to say the probability that Y equals Y, conditioned on R being R and A being A. But now I need to multiply by my probability that R is R, given that A is A. And now I want to invoke my independence assumption. So what does my independence assumption tell me? My independence assumption says over here, what am I allowed to do?
You drop the conditioning on A.
Yeah, I don't need to have this, or I can make a conditioning on B, yeah, exactly. So that is easy. So I can drop it, or I can make it A equals B, fine. So that's independence. Now over here, I want to use my sufficiency condition. How am I going to use my sufficiency condition? What is that going to do for me?
And also change A to B.
I am also allowed to change the A to the B. What does that mean? That I can change A to B here?
All this thing is independent of the value of A. That's it.
Yeah. Both of these things have this
So that means that the
independence.
left-hand side is independent of the value of A. That's Y is independent of A.
So that equals to the probability of Y equals Y given that A equals B.
Exactly.
That's what.
So all this independence had caught up with us, and we got stuck with independence that, whoops, we didn't want. So somehow, when you put those first two conditions together, there's like too much independence running around, and we end up in this situation where you can't have these sensitive attributes have any meaning. Okay. Now let's maybe make it a little bit more interesting. Let's think about independence and separation. Okay?
Okay, but Katrina, I want to go back to Norm's question.
Yeah.
Because
Which question? Sorry.
So Norm said before, and I strongly agree that our really greater problem as a society is situations where they are independent and we are still highly biased.
Yeah.
And I believe there are also many conflicts even in that situation, right? I mean, situation which is, you know, second
order issues.
second order
Yeah.
issues.
I think you're right. In some sense, we're here because that first situation is easy algorithmically. The problem that
But even there, we have some conflicts for different
we can, yes,
notions of fairness.
absolutely, because if what you're trying to do is something that is not reflect the statistical reality, but rather change the statistical reality, because you're trying to do affirmative action, because you're trying to sort of make up for historical inequalities, that's not captured in the notions we're playing with here, and that's part of the reason why we have, I think, these human conflicts over whether or not we should take into account some, membership in a protected group. People would be in favor of it in sort of the remediation direction, would say, yes, we should recognize that this group has historically had fewer opportunities, and actually we should give them more opportunities today. So some people are pushing in that direction, and other people have I'm not going to attempt to diagnose why, but inclination to give fewer opportunities to people from a certain group. And those are sort of pulling in opposite directions here. As long as we're not trying to do the sort of repairing of historical problems, then in some sense we have an easy algorithmic problem. And that's part of why we're here doing these second order questions. But I think you're right that it's worth reflecting that this means that in some sense our notions aren't getting at all of the fairness issues that we care about in society. Does that sort of go where what you were thinking? Yeah, you want to add to
I
that?
have a comment about it. I think
Yeah.
that when we talk about independence and stuff, we are also talking about the independence in the data that's available. And I think that it is not true that in the data that we have that that there is an underlying independence because of these historical injustices.
Yeah.
And it is, maybe actually there is very little independence, but I don't think there is full independence.
Yeah.
Like, I'm sure there are cases where there is very little independence in the data just because of that's how we have the data. And we still are like completely relying on the attributes and we should not be. That is maybe closer to what Noam and Michal are describing. But I feel like in many of the cases, the data that we have are like highly independent just because of the bias in the data itself.
Yeah, yeah.
But isn't bias in data kind of different from bias in the algorithm?
I think that there are different issues at some level, partially just because when you think algorithmically and in terms of, sort of stated optimization goals, the sort of tools that you can use to address both of these issues look different to me. But I think all of you are getting at a sort of cluster of issues that suggest that in some sense I've scoped the problem too narrowly. That you care about fairness, that maybe encompasses questions about where did that data distribution come from, or maybe even more broadly, questions like how do the incentives I build, for example, with the classification algorithm that I deploy, change the future distribution? And that's a whole rich literature of questions. You can talk about sort of strategic classification kinds of issues, and you can talk about these feedback loops in these deployed machine learning systems. Super interesting things to model and super important to acknowledge that the data distribution is not correct and it's not static, and in fact it can depend on the decisions we make in the design of these algorithms. So if I design an algorithm that provides no incentive for people from a certain group to invest in education, I should not be surprised that downstream I see in this data less investment in education. And you can have these self-fulfilling prophecies in some sense, and really interesting interactions. There's also a whole sort of sub-literature that looks at the composition of algorithms and investigates the situations under which giving a fairness guarantee of a particular flavor on an algorithm that has an output that is fed into another algorithm that has another, maybe the same fairness guarantee, whether you can guarantee fairness for the composition of these algorithms. And the answer is generally not. These things don't compose nicely together. And trying to understand when you can make these kinds of statements and what are the conditions you can get sort of composition results. But I think all of this is sort of a pull to expand the scope of what we're looking at. which is, I think, exactly the right direction to pull this literature in. And it's part of what the literature's been doing in recent years, is trying to say, can we model a bigger piece of the system? Can we look at these feedback loops? Can we look at these sort of longer term effects? Can we question things about the data? I have some work from a few years ago that looks at questions like, suppose in one group we just have noisier information about them than in another group. What can the consequences of that look like, and how can that manifest in significant sort of unfairness? So there are lots of ways that you can say, hold on, this is not enough of the issue in this model. Absolutely. There was another, yeah.
It's not really what's behind a lot of the legislation. So, Biden passed an executive order last year specifically looking at loan approvals, in particular dealing with the loan issues. We're talking about the bail software is still in use in most states, even though they know there's terrible problems with it. And the European Union obviously passed the AI Act that once again looks at credit scoring in particular. Do you think that holds much promise for solving some of these issues?
Well, none of these interventions are going to avoid these mathematical conflicts that we're running into here between the various statistical notions of fairness. So for example, with the COMPAS algorithm, the response to the ProPublica investigation was, well, I'm sorry we didn't, obey your notion of fairness, but our algorithm is actually calibrated. What do you want from us? You can't have calibration and your notion of fairness. And in some sense, in any interesting space, you're always going to be able to point to something that looks like some version of unfairness. And that's not something that you can resolve with an executive order. It's just sort of a fundamental mathematical impossibility that you can't have these, notions simultaneously. And so, yes, we're going to have to, in some way, navigate as a society decisions about the trade-offs that we strike between these various desiderata that include various fairness notions and include accuracy notions and include other things. But I don't think anything in the math really tells you how to strike the right trade-offs, for better or for worse. I mean, some things about the math really do make people prefer certain notions over others, but I'm not sure that those preferences and the sources of those preferences align with sort of societal preferences and desiderata. So I tend to think of the role of the theoretician in this space as to elucidate the realm of possibility and to elucidate the necessary trade-offs so that people with domain expertise and the general public can have an informed conversation about those trade-offs. I think, knowing the trade-offs exist is really important, even if it doesn't tell you, where to balance things. But definitely, in some sense, we're playing in a very small corner in a very toy model of a very complicated social problem. And it's disappointing how limited that is at some level.
Keep going back to the same problems over and over and over.
Yeah. But I do think even in this toy model, there are lessons to draw for very real applications, where you can see that sometimes there have been trade-offs struck that maybe would have been done differently if there was a greater awareness of sort of the realm of possibilities. Yeah. Yes.
Yeah, I feel like in practice it doesn't really matter at this form, because you approximate anyway. You train these algorithms, and since there will be some violations, maybe you just define an epsilon that is comfortable for you, and adjust the loss function such that either of the notions of fairness is satisfied approximately.
Yeah. So that's a space where there's actually been surprisingly little literature. There is some on sort of approximate versions of some of these notions, but actually I have a student who's working on a version of some of these questions. There are a bunch of ways you can approximate them. There are a bunch of ways you can sort of write different versions of some of these. It's not fully mapped, the interactions between all of them. In some sense, the literature hit up on these impossibility results that I'm going through with you guys now, and then went, oh well, and kind of moved on to other things. And I think there are still some sort of remains left to be picked up there to really sort of more understand the rich interactions. So yeah, absolutely. Yeah. Okay, so should we do another one? I think let's do independence versus separation, then we'll see if we have an appetite for the last one, which is the most interesting, but also a little bit richer, or maybe we want to move on to other things at that point. But let's look at our independence versus separation. Again, I promise I'll remind us all what all of these things mean again. Okay, so independence is again just this pure, clean independence notion. Separation is this sort of calibration-y thing that talks about the usefulness of these scores across groups. And so again, there's going to be the probability that R equals R, condition on A equals A, being equal to the probability.
Does the second one imply the first?
Great question.
If for every value of y, R and A are independent, sorry, no, the first one implies this. If R and A are independent, no, wait. For every
For
value,
every y, there,
No.
still dependent.
no, sorry.
It's a good place to get stuck.
Yeah.
Let's work it through a little bit more slowly. Yeah. Okay, and so our separation, let me just write our separation condition. Okay. So let's move to the binary worlds. And we're also going to require that R not be independent of Y. So let's claim for binary Y and R not independent of Y, then independence and separation can't have both of them. Why not? Okay, so first of all, why is this maybe an okay assumption to make? I want to say that R is not independent of Y. What does that mean?
We have some prediction power.
Yeah. So I'm not just outputting something trivial here. It has some meaning, okay? That seems like a reasonable condition. Fairness might be easy if I can output garbage. Okay, so why are we going to run into trouble trying to get our independence condition and our separation condition together? Any thoughts? We're going to get ourselves into trouble? Well, let's
Depends
maybe...
on Y.
Sorry?
R depends on Y.
Mhm.
It's not independent.
Mhm.
Y depends on A.
Mhm.
Hence R depends on A. Which means R can't be independent of.
Yeah, so you feel like we're gonna get this sort of chain of assumptions about independence that we're sort of gonna lead us to this issue. Yeah. Yeah, so let's push it through again by contradiction. Okay, so let's talk about R for a little bit. So let's write the probability that R takes on a particular value. Well, what do we know about independence? We know it doesn't depend on the I. There's some universal thing going on here for any particular R. So I can condition here for free, right? Okay, so now let me add up over all of my Y's. I can do that. And now I'm again going to do my standard trick of now I want a condition on the Y's, so I'm going to pull that over. And now I want to put the condition in here. Okay. What does separation let me do? Separation lets me,
Stop A to B.
I can swap A to B, or as Sergio wanted me to do, I can make it a universal, right? There's some universal value here.
They just drop A equals A.
Yeah. So let me just do that. alleviate the binary nature that I wanted to assume and see what that does here. That'll simplify things, and then we can step back for a sec. So what does this mean? It means that we've got, well, the summation becomes much more simple in a world where I have
So
zeros and
also
ones.
that thing with equals the same thing with times probability of y given y without conditioning on small a. That just again
Yeah,
the
so,
same formula as the bottom line, but it's also correct without conditioning on small a, which means that you get the same. That's just no.
sorry?
Probability that r equals
Mhm.
take the last line, just forget the a equals a. That's a correct formula. Just a complete probability formula. Yes.
I
So
see, I
now
see where you
compare
want to
the
go.
two, and the two, provided that thing is not a constant, then conditioning on A or not conditioning on A is the same.
Yeah,
That's it.
yeah.
That's an
But-
easy way to see it.
I think that's a good way to see that. Should we do it more slowly, or are people happy with that?
Just write the formula, then you'll see.
So Sergio wants me to do this way, so we
Sorry,
will.
no, you do it your way.
No, your way is nice. Okay, so Sergio wants me to do this way. You want me to say this is equal to sum. You want me to do what? You want me to just
Times probability that y equals y.
the probability that y equals y without the conditioning on the
Another
a.
condition, that equals, just put on the left side, probability that r equals r. That's a separate formula. It's good that you have the line in between.
Yeah,
Just on the left hand side,
Yeah, yeah.
that probability r equals r.
exactly.
Okay? Now compare the two formulas.
Yeah. Yeah. So that's it. I think that's a nice way to do it.
Provided that thing is not constant, that's why you need that r
Mhm.
is not independent of y.
Yeah. Exactly. So if we have the
Not fully approved, right? Because you can
Ah,
have,
it's not quite as step by step as I was going to go for, but I think it captures the intuition. If people are happy with the intuition, we can stick with the intuition. If we want to work through step by step to get to the full contradiction here. Preferences? Happy with the intuition? You're allowed to be unhappy with the intuition. Happy? Yes? Yes? Okay, so again, it's this sort of chain of independences that sort of creep up on us and get us into trouble. So in the world of separation versus sufficiency, maybe before then it's worth reflecting again about what the sort of calibration notion gives us, because it's a little bit hard to swallow. And so again, remember what this sort of sufficiency / calibration notion looked like. So there we have the probability that y equals 1, condition on r equals r, a equals a is equal to the probability that y equals 1, condition on r equals r, a equals b. And what I want to claim is that this is not just saying something about, vaguely meaningfulness of these predictions, but this is actually saying something about sort of the positive predictive value of your algorithm, and that you have this matching of positive predictive value. So in order to get there, and in some sense this is playing into familiar for some of you who come from more of this sort of machine learning world, questions about trade-offs between precision and recall. So maybe let's make this explicit so we can see sort of another way of interpreting this sort of calibration notion. So the positive predictive value, let's define it as being equal to p sub a times the true positive rate. Remember that we're in this world in which there's a universal true positive rate, and because we're going to be, let's see, should I write this? Then we can write this as TPR plus 1 minus PA
Why do
times
people,
TPR.
I know it's late into the talk, but why is it called sufficiency?
I actually don't know the historical origins there. That's a really good question.
Like, I don't understand the meaning of the.
I also don't. I always have to remind myself what it's called because I don't know why. Calibration makes much more sense to me.
Calibration makes sense, independence makes sense.
Yeah, separation makes
Separation.
sense-ish. It starts to be borderline on what you're separating from what, but fine. Sufficiency, I mean, I could try to tell you a story, but I don't know that it's the historical story. I could try to tell you a story that's saying that, you know, you don't need to know the sensitive bit. It's sufficient in some sense to see the score to understand that.
Okay.
Don't quote me on that. I don't know. It's a good question. Yeah, if anybody knows the story, yeah.
No, I have a different question.
Yeah,
I
yeah.
wanted to complain.
Okay, good.
I don't understand the denominator. What's written in the denominator?
Oh, you don't understand because I have a typo there.
You can't have TPR balls.
Yeah. There's a very good reason why you don't understand. Does that make more sense?
Yeah, but the rising also, okay, so it's.
Oh, you also don't understand my writing. That's a good complaint. Yes. What can I make more clear? So here, let me write what my PA is first. So this is just the probability that y equals 1, condition on A being A. Okay. So this is the fraction of people in the A group who are true positives. And positive predictive value is saying, look, if I look at, in my A worlds, I can look at all the people who I label positively and look at all the people who I label correctly positively. And I want to look at this ratio, right? Questions?
So is that like precision?
Yeah, so this is a precision notion. Yeah. So for some of you, that's the vocabulary that you use here.
So the TPR is a probability, okay, going with the order, just, that's a probability that what given what? Just, can you write it for me?
Yeah. So the TPR, I guess, would be that should probably be the probability that R equals 1 given Y equals 1. Yeah? And my FPR should be the probability.
Unconditional, the unconditional one. No conditional small a. That's a total.
Yeah. So this is the total. And the
No, wait, like, what's PA is conditional rate.
So something that.
Yeah.
that's
No,
why-
so that's equal. I mean, we're going to be in a world in a second in our analysis. Sorry, you're right. Let me condition on it for a second. We're going to be in a world where it's equal regardless of whether you condition it on it. But let me keep the conditioning for now. And then probability that R equals 1 given Y equals 0, A equals A. Yeah? And so then positive predictive value is in some sense, we have this denominator that is saying what fraction of the labels among people who are A's are predicted to be positive. And then the numerator of this thing is saying among the A's, what fraction are correctly labeled as positive. And we're looking at this ratio. That make sense?
Yeah, so the easy way to think is multiply everything by probability that A equals A. Then instead of that small PA, everything doesn't matter.
You do
both
this
on top
like
and bottom.
renormalization.
Then you have just the probability of that conditioning, and then everything becomes clear.
Yeah, exactly. So yeah, so
Okay.
essentially the thing to notice here is that the sufficiency condition requires in the end having equal positive predictive values across the different groups. So the sufficiency condition is basically saying it's a particular notion of accuracy, and it's saying that particular notion of accuracy has to be equalized across the various protected groups. Should we do that explicitly?
So PPVA should be equal to PPVB?
PPVA should be equal to PPVB, yes. I think I even said the letters in the right order. Yes. So then should we do that or should we move on to something else? Is that That's not obvious. At least I think it's not obvious.
Again, what is the statement? Can you just
The statement says that sufficiency requires matching of positive predictive values across
So
groups.
sufficiency is equivalent to PPVA being a constant in A. That's what you're saying?
Yes,
Okay.
yes,
Okay.
yes.
And that's in a sense for any threshold?
This is, sorry?
For any threshold?
What do you mean by for any threshold?
Well, this is defined like through, we're in binary world, I guess.
Yeah, I
ours-
moved to a binary world
No,
when
but
I was
ours-
looking.
Ours
Yeah.
continues, no?
Yeah, you can, feel free to have a general R, but I made my Y's binary.
Okay. No, ours is
but-
binary.
R is also binary, but what is 2 positive and 2 negative?
Yeah.
No, you're right. For this part, for this part, you're right. Good.
So it's binary.
Yeah. Yeah.
It's almost, if I'm not mistaken, it's a triviality.
Yeah, it's
Just
a
to
one
take
line
that
of,
in-
but
it's
just
completely-
filling everything in if everybody wants to fill in all the details.
Just write the condition.
And similarly, you automatically get matching of negative predictive value, which is a weirder object where you know, everything that was a P became a 1 minus P, and everything that was a
It's R equals 0 instead
TPR
of
is
R
a-
equals 1.
yeah, exactly,
That's
exactly.
So,
So you can, yes, it also has a name, but it's maybe a less interesting object. So when we bring sufficiency and calibration sort of in contact with each other, when we bring separation and sufficiency in contact with each other, I told you I couldn't keep track of what's what. So our second and third notions, when we bring those in contact with each other, this is useful intuition to carry forward. And I think maybe what I'll do is there's a statement that you can make in the binary world, which is very appealing and very nice. There's a statement you can make in the non-binary world, which involves a slightly stronger assumption, which I think you won't object to. But it's maybe a little... Should we do the general world or binary world? Pros and cons to each, but we only have time for one of them. General worlds, binary worlds, they both give kind of the same intuition. These two notions don't play well together.
I think just simpler than.
Do simpler. Okay, so binary world. Okay, so the binary world is not just simpler, but it's a sort of stronger statement. And the claim is for binary classification. So the Y's and the R's are both binary. Then if we have a non-zero false positive rate, so basically we're not perfect. Then I'm going to claim that you can't have both separation and sufficiency.
now, which we are still assuming that A and Y are independent, and also that R and Y
Are not independent.
are not independent. Sorry.
So,
what are you assuming?
I just
out
need
of the
my
many?
A and Y are not independent.
So the original.
Yeah, my
no.
global
Okay.
thing is still
You
hanging
don't
around.
need the one that you added on from the previous.
Yeah, no, I don't need that.
Okay.
At least I don't think I need that. Will catch me if I need it.
So what's the weaker result for general?
So the weaker result in the case where we're not in the binary world, I need an assumption about there being non-zero probability mass and a bunch of the sort of intersections between the various A's, R's, and Y's.
Okay, so not
In order
only
for-
non-zero false positive, right?
Yeah, but I also need some other places for there to be positive probability mass. And so, one way you can just say it is you can say that there's non-zero probability mass in every combination of these. It's not a terrible assumption, but it's not quite as elegant, I think. And there, once you have that, then you also get the same results.
Okay, you have a little bit of mess everywhere, which is reasonable.
Yeah, it's a little bit of mass everywhere. I feel like it's kind of an okay assumption. You don't actually even really literally end up needing it everywhere, but you chase it through to sort of specific have this matching of positive predictive value. And so what we need that across two groups A and B, such that PA is not equal to PB because Y and A are not independent. We want to see this positive predictive value matching. TPR, let's see if I can get all of this right. PA, TPR, R's, P's, P's, R's. PA of the FPR is equal to the same thing with B's. PR, PB, TPR, plus 1 minus PB. Okay.
And again, you can write TPR rather than TPRA, right?
I can write, sorry, say again?
You write TPR rather than TPR sub A. Because you have the condition that says that it's.
Exactly, so
one of
I
them. I have no clue which one is which.
exactly. Condition number 2 was the matching of false positive rates.
That's
It
a
has a
TPR
name.
is independent.
It's a separation condition. Yeah, it
Yes,
says
the
it's
TPR
the
is
A doesn't
independent.
matter. Exactly. It's the FPRs and the
Okay.
TPRs don't need to carry the A's and the B's. Exactly. Good.
Could you please remind us PA?
Yeah. So here, the PA was just the probability, given that you're a member of A, that you're a true positive. Yeah. And so this says that this positive predictive value is independent of the A's and the B's. And so, yeah, and we have these universal TPRs and FPRs because of the separation condition. And so now there are two cases, basically, two ways you could make this happen. What could be 0 or what could be 0 to make this happen?
And the sum also TPR and FPR are not the same.
Uh,
They can be the same. So if they are the same, then it cancels out and PA is different than PB. So they must be different. That's the first thing. And then you cannot have one of them being 0 because then.
Yeah, so let me slow down where Sergio is going briefly. So Sergio is saying, okay, look, there are two ways you can get here. You can get here by your TPR being 0.
Yeah.
That would be one option. What's the other option?
PA and PB is
But
okay.
exactly. So we could get there with our FPRs. What if our FPRs were 0?
Then PA equals PB, which is forbidden by the.
No. We have cancellation here.
Yeah,
See?
Oh.
If our FPRs were 0. So those are two ways we could get here, okay?
Yes.
Our TPRs could be 0, or our FPRs could be 0. And basically the way the proof goes is showing that both of those are going to get you in trouble. Neither of those are going to work. I think, given the time, my English is not to do like the 2 lines for each of those, but you can see,
you've already assumed you can't have one of them 0 by saying there's non-zero for the first group.
exactly, that was one of the assumptions, and that same assumption, you basically invoke it to get the other one through like one extra step. Exactly. Yeah, so basically, if you have an imperfect predictor, then you get in this situation where, again, you can't have two of these notions. And I want to save a little bit of time to sort of figure out where we're at this point. So we have these 3 notions. All of them are good things to use as red flags. If you design your algorithm, you check it on data, and you see that the percentage of women who are getting high scores is different than the percentage of women than men, you should ask why. If you see different false positive rates or different false negative rates across groups, you should ask why. If you see, that you're uncalibrated on a particular subgroup, you should ask why, or sort of, there's this post-processing to get to the calibration, but you know what I mean at this point. But you can't have all of them at once in any sort of reasonable, interesting situation. So you're going to have to pick what you mean by fairness. If any of these, you're going to have to make trade-offs. And that's kind of an uncomfortable situation, which explains in part why we continue to have these headlines that say, this algorithm's unfair, this algorithm's unfair, this algorithm's unfair, every interesting algorithm's unfair. And that's the kind of disappointing, unhappy bottom line of all of this, is that I don't know what fairness is. All of these, none of these, something of these in different situations, maybe, sort of, kind of, but you can't have them all. And even if you didn't like any of them, that probably should bother you at some level. Yeah?
Again, in practice, it doesn't matter because it's approximately. So, unless there's some statement that you can't approximately have them, they are contradicting directly.
Yeah. So there are statements that go in that direction, but there aren't enough of those statements that go enough in that direction with enough appealing versions of the relaxation. So that is absolutely a gap in the literature. And that's part of why I think that people gave up too soon in this space in some sense. I think there's more to be said here. One of the directions, though, that this literature has taken is there's been a sub-thread that has really, really embraced these calibration-derived notions, because they don't fight with accuracy. And so that they have this very appealing property. I don't know that they're super appealing as a notion of fairness. I don't know that I can make the argument that that is fairness in certain situations. But what happens in the calibration literature is there's a rich and really interesting literature that attempts to give you this calibration style guarantees simultaneously for lots of different overlapping notions of sensitive group membership. So I want calibration on men versus women and white versus black and on everything versus everything. And I can't literally do it on everything versus everything, as Sergio correctly pointed out earlier. But it turns out you can do this for extremely rich classes of notions of these concepts. And there are algorithms that operate in sort of very natural and efficient ways in order to produce these multi-calibrated results. In some sense, if you think of it, you can be in a situation where you can have an oracle that will show you a calibration violation if your current algorithm has one. You can use that oracle to rapidly improve the overall sort of multi-calibration here. This will sound familiar and evocative for some of you of things that you've seen before, and if not, don't worry about it too much. But basically, if you have an oracle that says, here's a calibration violation, you can use that to quickly converge to overall good scores here. And one of the nice stories in this space is this might be interesting and useful even if you don't really care deeply about the fairness interpretation of calibration, and you just care about the sort of accuracy sort of notion of calibration, is that this literature has sort of been applied also, for example, in trying to improve some of the protocols that are used in the Clalit medical system in order to do prediction, in order to do sort of decision-making about provision of care. They discovered that the existing algorithms were not well calibrated on certain subgroups, and they were able to sort of use these algorithms that emerged from the fairness literature to generate better algorithms, which have since been deployed. And so this literature has been having some impact, regardless of whether you think this is about fairness or not. It's been having some impact at least on accuracy. And maybe you also think it's a good thing that they discovered that there were certain populations that they simply weren't doing a good job of scoring.
But again, and I think Noam said that. I mean, you have full accuracy, then you don't care about it. Then fairness is solved. So in a sense, try to get as accurate as possible. Then in the limit, you get your fairness for free.
Well, surprisingly enough, I think not everybody would agree that if you have full accuracy, that's fairness. So let's have the following thought experiment.
Affirmative action, no, if you want affirmative action, you can. But that contradicts accuracy.
But what is accuracy? I think that is already not clear.
There's another definition of accuracy that says, to do with affirmative action, for example. So I come from Australia. If you look at repayment rates in the 1970s, women were paid 75% of men for everything, right? So you have these systematic partitions, however you want to think of them. There's the affirmative action, which is like, let's change the whole dynamic. Then there is the, we haven't allowed a population to express themselves properly. So the repayments a great example. Merit distributed between male and female academics, is a lot of literature on that. And it basically said, if you believe intellectual merit is equally distributed across the world population, which geneticists say it is, if nothing else, and biology says it is, then any unequal distribution you observe, if it was allowed to express properly, would be fair and would be correct. And so it's not even affirmative action, it's just giving the population the ability or space to express the real distribution.
So the question is, if R equals Y, is this fair or not? Let's start with that.
I think the
That's
answer is
questionable.
that is the.
You say this is
I mean,
questionable.
I think
it's
that's-
not I'm saying it's questionable, I say people say it's questionable.
There's certainly no consensus that a perfectly accurate algorithm is the fairer thing to do in all situations. We've been living today in this
But
little
you
bubble.
already said, you don't want to overcorrect, to correct for the past.
Today I didn't want to, but
Yeah,
maybe you
that-
do in other
that-
situations.
That means correcting for the past, correcting for some other problems, but that's not the algorithm issue, that is a social problem. Now, if you want to put on top of the algorithm some other properties that you want to correct the world, to make it a better world, that's something else, but that's not fairness. That's a
Many
different-
people would argue that it's exactly fairness, thinking about
Not fairness
how,
of the algorithm, maybe it's fairness as a general notion, let's live in a fair world,
but it's,
but not let this algorithm be fair. We should separate that.
I think there's an important point though here that it's,
No, I mean,
that,
again, I'm not
that we
advocating
can't,
that. I'm just saying that one should understand what is the aim.
that if we analyze just the algorithm in isolation, we miss the broader picture, and fixing the algorithm in isolation may not result in a fair system in which that algorithm is deployed. And that's a major sort of point that is actively being investigated right now. I'm sort of remotely supervising a master's student who's looking at this in the context of machine translation. All the work on fairness in machine translation is talking about inside the sort of technical object, looking at various notions of fairness there, and she says, hold on, this is then deployed in a system where there are humans who then post-process the output of this machine translation. What's the interaction in terms of fairness of the overall system?
No, but that's
That's
outside the scope.
outside
of
the
this
scope
design.
of
No, but-
today,
okay,
absolutely,
no,
but
no,
there's
but
sort of
that's
this
still-
broader
But
picture.
let's go back to the simple case.
Yeah.
I know why. I got a peek at why. And you tell me that the outcome of the algorithm should be different than why. Why?
Why?
Right.
Why? What should it be? Tell me what should it be?
So
What should it be?
that's-
I mean,
I think you're missing the point here.
okay, so tell me what it is.
Um,
I'm arguing. That's, yeah.
Yeah, so accuracy in practice is not one, right? It's like there's some maximal number.
So I said, we have perfect accuracy. I want to take
We
the
have
extreme
a
case.
crystal ball
I
that tells
will-
us
Mathematically,
the
let's stop,
almost.
because if we don't agree on the extreme case, we
Yeah.
are not going to
Okay, no, I agree.
on when
With
we are in the
extreme case.
middle. So now I'm saying, look, you got a peak, you know why, you can have R equal Y for everybody. Now, is that a fair outcome? Is that a fair algorithm or not? We have to, because if we don't agree on that, we won't agree on anything else. I think.
Yeah, I think we agree in this simple picture. If we don't go out of scope as you
If
described.
everybody agrees that Y is true.
If everybody agrees
Yeah,
that we
there's an
have
objective
historical
one. There's an-
data that is exactly what we want to replicate in some sense. So the Y is measuring the thing that we care about, it's correct, the distribution is the distribution that we continue to live with, and we want to replicate the historical data, then fine. But I think all of those ifs that I just said can be called into question in lots of situations. Maybe the data is, not accurate, maybe the Y is not the right objective, maybe.
Those are-
No.
yeah,
Even
you
without
are-
that.
you are- once you complicate it, I agree, but let's.
No.
first agree.
You can look. So my point is, you cannot have an implication that just maximize accuracy, because in this extreme case where accuracy is one, it's not the real world case. And in the real world case, you have local minima or even several global minima. They
But
can
let's think we are in an ideal world, and let's agree what we call fairness in that world. If we, what my claim is that if we can't agree on fairness in that world, then we are never going to agree in any other world.
I think we're never going to agree, so I'm willing to accept that.
Yes.
But
Efficient allocation.
That's the one
Okay.
thing we can agree
So
on.
never
I think
agree.
we can end with agreeing to disagree here. You wanted to add one more thing?
No, so I think it's, you know, Sergio is giving one example, but I think the criterion that is kind of missed is that, you know, we can always do, even if we can do Bayesian prediction, this might not be, like you're suggesting, it would be Bayesian. It's perfect in this case because you know the why. It might not be desirable for other reasons,
Okay.
right? And this is what this literature
That's what I said, we
acknowledges
want to
that
be in a better
that
world.
there is
than
some
what it is.
social objective function
Right.
that is
We
different
want
than
everybody to
prediction.
repay, everybody
And
to
we
be
can
able to repay their loan.
we can
But that's not
disagree
right.
on what it is, right? That's all, right? We
Yeah,
can
but that's
disagree.
outside what the algorithm should do.
So I think maybe let's wrap this for now and invite you all to continue the disagreement in the hallway and throughout the rest of the week.
I think
Thanks,
that's
everybody.
a fair summary.